Hello everyone, today let's take a look at a pretty tricky question, Quantipus number 7. So given endpoints drawn randomly on the circumference of a circle, what is the probability that they all lie within a semicircle? So what exactly is this question asking? Well, let's just say that, for instance, I placed 5 random points on the circle. And in this case right here, I can see that they all lie within a semicircle, right? If I draw this semicircle, then every single point's on one side of it. If instead my random points look like this, well then yes, again, I can fit them all in a semicircle, because if I split my circle into halves like this, well then every single one of my points lies on this side of it. However, in this configuration, there's no semicircle that I can draw such that the points lie on the same side of it. So now let's actually find the probability of every point being on the same side of the circle. So obviously, trivially, if I have one point on my circle, well then it has a 100% chance of lying within the same semicircle as every other point, because there's only one point, obviously. So let's say 100%. Now notice that if I add another point in and I have 2 points, well there's no place that I can place it such that these points do not lie within a semicircle, right? If I place it here, they're going to lie within this semicircle. They're both on this side, no matter where I place it, right? Even if I place it completely opposite to this point, well then technically they're still on the same semicircle. So for n equals 2, we also have 100%, but that's kind of where it stops being that easy, right? We're going to go up to n equals 3 now, and let's figure that out. So now you can pretty clearly see that our probability is not going to be 100%, so now it's going to get a little trickier. Okay, so how do we approach this? Well, obviously we're not going to be able to check every single diameter that goes through this circle, right? Because there's infinitely many of them. But we really don't need to check every single one, because if you notice, and really the key thing to notice, is that we only really care about the diameters that end at one of our points. So for instance, these would be what they look like in this example. And this is because if every point lies on one semicircle, well, there's going to be a leftmost point or a rightmost point, depending on which direction you're thinking about. So we only really need to check these 3 blue diameters that I've drawn in one direction that we fix. Okay, so let's go through case by case. If this point were my leftmost, well then every single other point would have to lie on this side of it if I fix this direction. I could have also fixed this one, but just for this example, I'm going to fix this direction. You can see that our conditions are not satisfied, right? This is on the other side of the semicircle. So now I would move on and I would check this point. Okay, if this one were my leftmost point, well then everything should lie within this side of the circle, but they clearly don't. So now let's move on to my next point, right? If this were my leftmost point, well then everything should lie on this side of the circle. However, again, this one's on the wrong side, so we fail yet again. So now we've checked every point as being the leftmost, and we know that one of these points must be the leftmost if everything were to lie within a semicircle. So now we know in this specific example, there's no semicircle that cleanly partitions our points. Also, sorry, just realized I've been saying leftmost a lot, which doesn't really make sense in the context of a circle, but you can just imagine that we're picking a direction, I guess counterclockwise or clockwise. Okay, so now let's think about the probability of points lying within a semicircle of each other. Well, in this case right here, well, that would just be the probability that all of these points lie within this one, or they lie within this one, or they lie within this one. So to put that in probability terms, if I labeled these points 1, 2, and 3, and I define these events L1, L2, and L3, where L sub I is the event that the points lie within X sub I's clockwise semicircle, right? This, what we've been doing here. Well, then the probability that we're looking for, right, let's call it the probability of E, well, that's just equal to the probability of L1 union L2 union L3, right? Because we're going through all of our quote-unquote leftmost points, and we're saying if we start a semicircle here and go in this direction, then what's the probability that every point lies within this semicircle, or every point lies within this semicircle if we choose this one to be our leftmost point, or every point lies within this semicircle, right? So now what do we know? We're taking a union of a bunch of sets. Sounds like inclusion-exclusion, doesn't it? So if I write out the inclusion-exclusion, obviously I get this. Okay, so first let's calculate these, the probability of L1, L2, and L3. So first, let's say I fix L1 and I'm checking this direction right here, right? This side of our circle. Well, now what are the odds that both of my other points lie on that side? Well, the circle splits the diameter in 2, so there's a 1/2 chance that we're on this side. And once I fix this point, I have 2 points remaining. So the probability of L1 is just going to be equal to 1/2 squared, right? Now, if I fix X2, it's going to be the same story. What are the odds that both of my other points are on this semicircle? Well, again, 1/2 chance for each of them, and there's 2 of them, so 1/2 squared as well. And it's going to be the same deal for L3 as well, right? So 1/2 squared 3 times. Okay, so now let's talk about the probabilities of intersection, which is the second key thing that we need to understand. Okay, to talk about intersection, let me use this right here as an example. Obviously, you can see that all these points are on the same side of the circle. So let's ask ourselves, what are the odds that it's true at the same time that all points lie within this point semicircle and they lie within this one's? And you're going to end up finding that these events here are mutually exclusive and there's 0% probability for all of these intersections, right? And the reason for that is, imagine one of my points has every single other point within this semicircle. So every point exists in this upper hemisphere, but if I draw any other diameter and I check in the same direction, well, then you can clearly see that this point is not going to be included within that check. So if we're checking in a sequence like this, well, the only time that this one will get included again is when we check the one directly across from it, or another one on this hemisphere. And clearly, by the time this one gets included, right, all the other points up here will be not included because now we'll be looking at the lower hemisphere. So therefore, these intersections right here are all going to be 0. It can only be true that the points lie within the semicircle created by one of our points at a time. So therefore, in this case, our answer is just going to be equal to the sum of these, which is equal to 3 on 2 squared. So that's equal to 3/4, and also a pretty easy question to generalize to n points, right? If I have n points on my circle, I'm going to have n different points to check as the starting point for our semicircle. And for each one of these n points that I check, I'm going to have n minus 1 remaining points, and each of those will have a 1/2 chance of being on the same side of the semicircle as the direction that I choose. So n on 2 to the power of n minus 1. So this is our final answer. You can see it checks out for the n equals 3 case, which would have been 3 on top and 2 to the 3 minus 1, or 4 on the bottom, which we got. Also, you could check for n equals 2 and n equals 1, and both of them will give you 100%, just like we expected. So yeah, definitely a tricky problem to visualize. The conditional probability was coming in when we were checking these. We were fixing a point, and given that that point is fixed, we were calculating the probability. So yeah, this question ties in a lot of things we've been doing, right? Conditional probability, sets, inclusion, exclusion, and symmetry. So at the end of the day, I don't really like this question, as I don't like most questions involving circles, but this is just a good one to know.